Okay. So last time we studied about the path independence, or like, and the existence of the antiderivatives. They were mathematically equivalent. So that was our big theorem from our last lecture. And please allow me to summarize the state theorem. So it goes like this. Suppose that f is a continuous function on some domain D, then the followings are equivalent. So number one, so f has an antiderivative so I would say large F on D, and the definite integral is, the path integral is just merely the evaluation of the antiderivatives on these two endpoints, where C is a curve on D from Z1 to Z2. And so number 2 is basically saying about the path independence of the line integral. And for number 3, for if C is a closed curve, closed curve in C. Sorry, I messed up. A closed curve C in D. Yeah. Okay, so that is basically the main theorem of my previous lecture. Okay. All right. So let us work on some couple of exercises before we move on to next section. Okay, so I just came up with some random curve, which is from I over 2 to I, and say my curve is traveling from this point to that point and oriented like this. And also say that my integrand function f of z is e to the pi times z. Now, so what do you think is this line integral? Okay, so yeah, okay. So obviously, so the exponential function is an entire function. I mean, so this function is analytic for in entire complex plane. So it suffices to find the antiderivative of the function. So what is obviously the antiderivative is 1 over pi times e to the pi z, right? So e pi z, and evaluation on I and I over 2. And and the rest computation is very straightforward. So I'm not going to do this. And the answer is just 1 plus I. All right. Another exercise. And where C is a unit circle Well, as always, radius 1, center equals to 0, and positively oriented. Okay. What do you think is the answer? Well, I believe the antiderivative and integrand, which is 1 over z squared, I guess so domain of this function is the entire complex plane minus the origin, right? And I believe on that domain, the function allows its antiderivative, which is minus 1 over z. Okay? So, and since the curve is obviously closed, therefore, I guess the answer equals to 0. Am I right? Yes. Actually, this is right. Yeah. Then, yeah. Okay, so if you believe in the theorem, then yeah. And then you must be pretty sure that the answer equals to 0. Okay, so what about the next exercise? This time, so let me switch my integrand function from z 1 over z squared to just 1 over z. What do you think is the answer? Does it have antiderivative? Yeah, what is the antiderivative of 1 over z? It must be natural log function, right? So I guess the answer should be 0. Yes? No? No. In this case, the answer is no. Hold up. It looks like this function, this exercise satisfying all the conditions above. So the answer should be 0. But why this answer is not 0? So in fact, as a matter of fact, the answer turns out to be 2 pi times I, which is clearly not equal to 0. And the answer is, so for the natural log function, so well, you cannot take any multi-values function as an antiderivative. So in order to choose some function as an antiderivative, then actually you need to choose the branch. And in order to choose the branch, then you actually need to make a branch cut. And no matter which branch cut you choose, then however, your branch must be something like this. Your branch cut must be something looks like this. So therefore, the domain of this antiderivative is actually does not contain the curve C, right? So it can never be able to contain. So no matter which branch you choose, but your domain of your branch function can never be able to take the curve of interest, this unit circle, inside the domain. So this is the reason that why you cannot change, you cannot make use of this theorem. And also this is the reason that why the answer is not a non-zero number. Okay. So this is 2 pi I and non-zero. Okay. So now today I want to discuss something more about on the path independent line integrals. And in order to do that, first I will need to introduce you a notion of the simply connectedness. Have you ever heard about the simply connected set? So, well, well, suppose that I have chosen some subset from complex plane, which I will call B, and I say this set is B is called simply connected. If any closed curve in D can be, yeah, this is very important point, can be continuously shrunk to a point throughout the, what do I mean by, so any closed curve can be continuously shrunk to a point? So, well, so roughly speaking, so this condition implies that, so in order to be simply connected, then your set does not have any hole inside, right? But well, if this is my set D, then you can just think of any curve contained in this set D, and this curve can be continuously shrunk to a point. And this is true for any choice of closed curve in D. But however, suppose if your set D has at least one hole inside, then for this curve can be continuously shrunk to a point. But in this case, you can actually usually be able to find a closed curve completely contained in D, but this guy can never be able to continuously shrunk to a point because, there is a hole inside and you can never be able to pass this hole, right? So this is the idea of the continuous simply connectedness. Okay. And okay, now we are turning to the next section, which is 14.2. This is about whose title is the Cauchy's integral formula. So I will begin from the Cauchy's theorem, and it goes like this. I have a set. So this is actually domains connected and open subset in D, BA. And I assume that D is a simply connective domain. This is very crucial factor. This is very crucial condition. Domain in complex plane C, and also I let a curve C to be a closed and oriented curve contained in D with also lastly FB and analytic function on the domain D. And on top of that, we assume that F prime is continuous. Oh, sorry. So, yeah, I should clarify myself. Let us assume that U and V are continuously differentiable. Okay, yeah, I have lots of conditions imposed on the. I actually need lots of conditions. Then the conclusion is so. So basically, so as long as your function is analytic and your curve is hold on. I think I need just one more condition, one extra condition. Yeah. So I'm sorry. So simply closed and oriented. Okay. Sorry about that. Yeah. I just missed one more condition. Yeah. So you know what I mean by simply closed? Well, a closed curve is simply closed. So that means it doesn't have any self-intersection. So if your curve does not intersect itself, then we say that it's simply closed. Yeah, under this last of hypothesis, and the integral, the dispense integral always equal to it. Okay. Okay. So hey, hold on. So what is the meaning of this continuously differentiability? So U and V are continuously differentiable, and well, as always, U and V, we are assuming U and V, these are real values functions depending on the x and y, and they are continuously differentiable means that so they are partial derivatives. Ux, uy, vx, and vy, they are all continuous functions. Then the answer equals this. Yeah, and this integral equals this. Okay. Oh, all right. Okay. So let me prove this. So since this is a theorem about the path integration, so the first thing that I will need to do is I will try to choose a parametrization of the curve C. So Z is, and well, maybe the T must be some number between A and B, a parametrization. So, and because of our definition, so it should be the integral from A to B f zt times z dot t and everything dt. Okay, now I will try to expand this expression just a little bit. So u xt yt plus I times v times xt yt. Yeah, xt yt means just parameterization zt, and everything by x dot t plus I times y dot t and dt. All right, so okay, so maybe I'm getting tired of putting this xt and yt, so please allow me to drop these numbers. So I will just write these things as u times x dot minus v times y dot, just times everything dt, and plus I times ab v times x dot plus y times, sorry, not y, u times y dot. everything dt. Okay, so well, I ended up this some sort of very simple expressions like this. Oh, these the last expressions reminds me of something. So do you remember? So what we did? So when we were in the multivariable calculus course, then we tried to find a line integral over a vector field, and this expression is precisely represent the line integral of the vector field. Line integral of which vector field? So this is actually means the line integral of a vector field u whose x component is u and y component is minus y. The TDS. Okay. This is the first expression precisely means the line integral of vector field whose x component is y and y component is, sorry. Oh, I messed up. Minus of v. Sorry. Yeah. So this is the line. So this is the vector field that we are working on. And for the second term, I times this is the line integral whose x component is v and y component is u. All right. Now hold on. So now I will make use of this simply closed condition and simply connected condition. Why? Because okay, so please allow me to draw some little picture of this. This is domain. This is my domain, which is obviously simply closed. And my curve is also simply closed, contained in the domain, like this. Okay. And since my curve is simply closed, therefore, my curve must be bounding some sort of simply connected region that is completely contained inside my domain D, right? I'm going to call this region maybe R. Yeah. So this is a closed region bounded by my curve of interest, C. And now this is my best time to take advantage of the Green's theorem. Do you remember that? Yeah. So what was the Green's theorem? Yeah. For those of you who do not remember the Green's theorem, so yeah, this is a quick reminder. So this is the Green's theorem. So if a simply closed curve C bounds a simply connected region R in R2 and a vector field whose x component is P and y component is Q. A vector field P and Q is continuously differentiable. Then the Green's theorem says the line integral over this vector field is the same as double integral, the y component taken derivative with respect to x, and the x component taken the derivative with respect to y. So this line integral must be the same as this double integral. So that is basically the Green's theorem, right? Okay. And well, luckily, so since we are assuming that these two guys, U and V, are continuously differentiable, so, and this guy is simply closed, and this simply closed region is actually bounding a simply closed, the simply closed curve bounding simply connected region. Yeah, it's still confusing. So, okay, the first term over here should be the y component taken the derivative with respect to x minus this is x component taken derivative with respect to y dA and plus I times double integral over the y component, which is u, taken derivative with respect to x, minus the x component y dA. Okay, all right. Now, finally, now I am ready to make use of this analytic function, this condition. Since my function is analytic, so therefore it must satisfy Cauchy-Riemann conditions, and therefore this guy should be 0, and this guy also should be 0. Okay, great. So, yeah, my proof is done. This is the Cauchy's theorem. Okay. Right. So great. So combining this theorem with the theorem that we studied in my previous lecture. So this implies if your function is analytic in some simply connected region, then it must have some sort of anti-derivative on it, right? Because so well, even though we are working on even though this theorem is true for a simply closed curve, but you can actually generalize this result for, but even if your curve has some finite number of self-intersections, then you can actually break down your curve into a bunch of simply closed curves. Therefore, you can easily generalize this is true for a multiply closed, not a curve which may not be simply closed, but this, you can actually convince yourself this is true for possibly non-simply closed curve. And then that actually implies that your function has an anti-derivative over it, right? Okay. This is very satisfying answer, and which can be derived from the fact that f is analytic function. But I actually want to refine this theorem even more. So that is, I want to drop the last condition. So what last condition? I mean, so in the last line of this bunch of hypotheses, so I assume that my function must be continuously differentiable. So it turns out this last condition of being continuously differentiability can be dropped out from the hypothesis. This is actually very important. Well, so if you have your textbook, then this is the proof that given by our textbook. But and in the last line of theorem, so in the last line of the proof, and the author says that this continuously differentiability condition may be dropped, but the proof is very involved, so we should omit it. So that is the author's idea. But I believe giving you the proof without using the continuous differentiability is very important. Why? Because in the real world, you can actually think of some function which is differentiable, but whose derivative may not be continuous. So this is why we're using the notion of C1 function or C2 function or Cn function. So you can actually think of a differential function, n-time differential functions, but whose nth derivative may not be continuous. there is such a function in the world of real analysis. But for the complex analysis, if your function is analytic function, then it is guaranteed that your function is also your derivative is also analytic, and that derivative is also analytic too. So so whenever you prove your function is just one time analytic, then that actually implies that your function is infinitely many times different complex differential. So this is the crucial difference between the real analysis and complex analysis. And in order to do that, then I feel like it is very imperative to get rid of this finite condition. Okay. So from now on, I'm going to give you the proof that doesn't require this last condition of continuous differential, which is for the quotient Borsas theorem. The guy who actually recognized the guy who first recognized this last condition may be dropped is the Professor Borsa. So because of this reason, so nowadays we are calling this theorem as a quotient Borsas theorem, and it goes like this. And if F is analytic, on a simply connected domain D, then for every simply closed curve C in D, so in order to celebrate the Professor Borsa, so we name it the quotient Borsa condition. And as you can clearly see from the statement, so we now have just dropped the hypothesis of continuously differentiability. All right, so what is the idea? So the idea goes like this. Well, this is a complex plane, and this is the domain. So this is a simply connected domain, so which our natural, and I say this is my closed curve C, simply closed curve C. And since my curve is simply closed, and so therefore my curve C must be bounding some simply connected region that is contained in the simply connected domain D. Okay, so the region inside enclosed by this curve I will call R. And what I want to do is from now on I'm going to divide this region by some tiny little squares. So these are squares. So length of the length of this side equals to length of that side. And well, even as long as your square is completely contained enclosed by curve C, then this is a square. And well, if that is the case, then well, so length of this side equals to length of that side, and their dimensions are all the same for the squares that lies inside of this region. And I'm going to say these are just squares. And just for these guys, so for the case when your square is intersecting on the boundary of this region, then I'm going to say they are the partial squares. But however, for simplicity, I will just call them squares. And these are, I would say these are sigma 1s, sigma 2, and sigma I, and so. So, so this is bounded region, and these are like squares with finite areas. Therefore, I must be able to break down this entire region by finite number of squares and the partial squares, right? So there is, I can find a finite many squares that covers the region. Which we call these cover. I would say these are rectangular covers. Sigma 1, sigma 2, sigma n. Cover of R, which I will denote by a scripted R. Okay, now I have a lemma that goes like this. For every small number, epsilon, so there is a rectangular cover, scripted R, R, such that in every square of the rectangular cover, there is a point GI contained in this rectangular, contained the sixth square, satisfying Fz minus Fzi divided by Z minus Zi minus F prime of Zi is less than epsilon for all Z in the sigma I. And okay. All right. This sounds very complicated because this is a compound mathematical statement. So. Okay, but let me try to analyze the state one line by line. So just choose any epsilon. Then you can actually find a cover, rectangular cover of the region R, bounded by curve C, such that for this cover and for every square, you must be able to find some point inside of the square, such that, and for that you must be able to point Z of, which I will call just Zi, and satisfying this inequality. And this inequality must be true for all these other than Zi, and this magnitude of this guy is less than the epsilon for every point on that square. Okay, so, well, if your rectangular cover is not fine enough, then you may not be able to find such a point Zi for some squares on the rectangular cover. But however, so in that case, you can make your rectangular cover fine enough. Then you can find all such a nice point Zi from every sphere in that rectangular cover. That is the claim of this lemma. Okay, so let me try to prove that. This is one of the most crucial lemma. This is the most important lemma to prove the Cauchy-Gorsas theorem. Okay, I'm going to prove this by using contradiction. Well, we choose any rectangular cover. Choose. Suppose not. Okay, so suppose not, that means I have to actually negate the statement given by the lemma. So what does it mean? So that means there is some very specific epsilon. And for that epsilon, then once you choose that epsilon, then no matter how fine your rectangular cover is, and no matter how small your square is, then you must be able to find one of that square, one square, that does not allow such a nice point Zi. Satisfying this condition. So, okay. So then, you should find a square sigma 1. I'm going to say just sigma 1 of the rectangular cover that doesn't have the point. I'm going to say the nice point. Okay, so yeah, so this square. Yeah. So let me say this is my sigma 1. Now, what I want to do is this. I'm going to subdivide this square into 4 equal squares, like this. Now, well, actually, not only dividing this single square into 4 pieces, but actually, I am making entire rectangular cover into I'm going to subdivide entire rectangular covers into these subdivisions. So every square, the area of every square in this new rectangular cover is most likely just 1/4 of the original, right? Okay, now let me focus on these 4 squares. Since you cannot find such a nice point Z in it, so therefore, for these 4 points, for these 4 squares, there must be at least one of these squares that cannot allow such a nice point, right? Inside. If so, then that means you can find such a nice point for that epsilon, which is clearly contradiction from this negation of the statement. That means that therefore at least one of these 4 squares, you can find at least one square. I will say this guy. So this guy is there. So this guy must be a square that does not allow such a nice point inside. Right? So and there, I'm going to call this guy to be sigma 2. So these 4 small squares, there must be a point. Sorry, a square, which I will call sigma 2, that doesn't have the nice point. nice point, I mean by the point satisfying this inequality. Okay, so this is my sigma 2. Okay, once you have chosen sigma 2, then I can also do the same thing. I can subdivide this sigma 2 into another 4 the squares with same dimensions. And for again, I'm going to use the same trick here. So among these 4 small squares, so I must be able to find at least one square that doesn't allow such a nice square, right? So, and if I proceed like this, then I must be able to find a sequence of squares. Proceeding like this way, I can find a sequence of squares, sigma 1, sigma 2, sigma 3, and da da da. Okay, why? Because since we're negating the statement from the lemma. Okay, so and I can find very interesting properties on the sequence of squares. And sigma 1 is the largest one, and sigma 2 is the smaller one, which is contained inside sigma 1. And sigma 3 is even smaller than sigma 2, right? And sigma 3 is also contained in sigma 3 is also contained in sigma 2, right? So this is actually I am just copying and pasting the technique that we use in the nested interval theorem. Do you remember this? Suppose that you have a sequence of closed sets, and if your sequence of closed sets are nested, so if you're nested, then you must be able to find the intersections of all such a nested interval at least contain one point in the entire intersection. That is the nested interval theorem. And that is true for, this is a 2-dimensional version of the nested interval theorem. So what I want to do is I want to find a point that lies in the intersection of all such squares, right? So let us consider a point well, these squares they are all closed, and their lengths, each side of each of these squares are like diminishing by a factor of 1/2, right? 1/2. So therefore, it's getting smaller and smaller and smaller, and therefore there must be precisely one guy that lies in this bunch of intersections, these infinite intersections, right? I'm going to call this guy to be Z of 0. Okay. All right. Okay. Great. Yeah, we are almost done. Again, so I was able to find some point somewhere over here. I don't know, maybe on somewhere over here. And also I am making use of the fact that this region R, this region is a region bounded by this closed curve C, and these regions R must be closed, right? So every accumulation point inside must be lying in the region R itself because R is closed, right? So, and since R is closed and Z0 is an accumulation point, in B, in R, so Z0 is contained in R, and at the same time, Z0 is contained in the domain D. And our assumption says that my function f is analytic on this entire domain D. So therefore, my function f must be complex differentiable at this point. Okay. So also, f is differentiable at z0 implies that for this epsilon, I can find I can find a positive number delta such that if is less than delta, then fz minus fz0 so I must be able to find such a nice delta satisfying this inequality. Okay, now I'm getting close to the contradiction. What contradiction? Okay. So this is a clearly contradiction. Why? Because okay, let me say my point z0 is somewhere around here. And I have some definite positive number delta. And let me say the radius of delta is just this much. Okay. Is it a contradiction? Yes, this is contradiction. Why? Can you see this? Well, so that means, well, if your index of sigma is large enough, then you can find some square which is completely lies inside of this delta neighborhood of this point z0, right? And on this delta, and because of this, for that sigma with a high large index, then you can actually find such a nice point in that sigma, right? In this field, and which is the clearly contradiction. So for sufficiently large K, there is a sigma K from the sequence of squares. And you can find a nice point in sigma K, which is contradiction. All right, great. Finally, so the proof is done, and now we are ready to I'm ready to give you the proof of the Cauchy-Gorsas theorem. All right. Okay, so now, so for any epsilon, and we have a rectangular cover R of R, whose existence is guaranteed by the lemma, previous lemma. Sigma 1, sigma 2, sigma n. So, well, so don't be confused. In this case, so sigma 1, sigma 2, sigma n, so that means I have a bunch of these guys. So let me say this is my rectangular cover. Oh, right here. Then for every square sigma j. Now we want to define a function which I will call delta of j, and define to be the fz minus fzj by z minus zj minus f prime of zj. And a function on. So if z is different from this nice, the existence of such a nice point z of j is guaranteed by the previous lemma, right? And if not, so if z is the same as z of zj, then we define the function to be 0. So this is our definition of the. This is a function not defined on this entire region R, but this is a function defined on a single square. So this is function defined on a single square on sigma j. And I want to claim that this function delta of j is continuous on entire sphere sigma j. Why is that? Because if the point z is other than z of zj, then well, all these functions involved here. So this is some constant, right? And this guy is constant, and these are some just polynomials or polynomials, and since therefore, if z is other than zj, then this is continuous, right? Because of our assumption, right? And fz is always continuous. Okay, should be continuous analytic function. And if z equals to zj, yeah. Now we need to consider a little bit. As z is getting closer to zj, then delta of z, since, well, so my function is defined, is assumed to be analytic, therefore my function must be differentiable at this nice point. So that means this guy should be 0, right? Because f is differentiable on zj. So delta of j is continuous on every point in this square. Okay, great. And on top of that, also the magnitude of delta j of z is always less than epsilon. Why? Because, well, since we are choosing the choice because of the nice point, and our lemma guarantees that this guy, the magnitude of this guy is less than epsilon. So therefore, this guy is less than epsilon. And when z is zj, which is 0, and clearly this is also less than epsilon. So therefore, this inequality is true for all z in this square. Okay. Now I'm going to say that Cj is the boundary of delta j. So this guy. So if this is your square, and this positively oriented boundary of this square should be your Cj. On this boundary curve Cj, So I'm gonna do a little algebraic trick over here. What is this? So on CJ, yeah, clearly the point on CJ must be other than the VJ. So therefore, this equality must be true. This delta of J must be same as this guy. So moving this guy to the other side of the equality. So delta J of Z, Z minus ZJ is FZ minus FZJ plus minus, yeah, should be, yeah, sorry. Minus F prime of ZJ and Z minus ZJ. And I want to solve this equation for F of Z. So this is FZJ okay, so this is must be plus yeah, Z times F prime of ZJ minus ZJ times and plus this guy just carries over. Okay. All right. Now I'm gonna take the passing line integral of the function along this boundary curve. Then what now? I'm gonna combine these guys and these two guys because these two guys are completely independent from the function. It's a variable z. So fzj minus zj f prime of zj. So I mean they're just constant, you know. Cj and just dz. And well, this is different. So this is a variable and this is constant. So f prime of zj integral over c along cj z dg and plus cj z minus zj times delta z like this, just like this. Okay, yeah, getting more and more complicated. Okay, so thanks for your patience. Yeah, we are almost done. And this guy is what? What do you think is this guy? Well, this is a closed, positively oriented closed curve. And well, the integrand function is just 1. And what there is clearly, we have clearly antiderivative of 1, which is z, right? So therefore, this guy equals to 0. And what now? What about this guy? This guy also allows the antiderivative, which is 1 over 2 times z squared. So its passive integral over the closed curve should be 0 too. So only this guy survives from the right-hand side. Okay. So and j is from 1 to n. Now I want to take a summation of this bunch of line integrals over j. Now, the amazing thing happens for the left-hand side. So what is this? So Yeah, so I just go back to this picture. And for each of these squares, I am taking the integral over the positively oriented boundary curves of each of these spheres. You know what? And well, for every side, for every side of this square, this side has been integrated twice, one time in this direction and other time in that direction, right? So therefore, every shared boundaries between the squares, they must cancel out each other, right? Therefore, after all, the only non-zero number out of this huge summation should be the integral over this boundary curve of this boundary curve, which is C. So this is okay. So I want to show that this guy must be 0. I want to take a modulus of this number. And since triangle inequality, I have this guy is greater than this. Okay, so actually I will need to, since I have like many terms over here, and I will need to consider two different cases. The first case is when the Cj is a part of the perfectly defined sphere. And the other case is when Cj is the boundary curve of the squares on the boundary of the region. So I mean, for the case when this guy is the boundary of the partial squares. If Cj is a square, doesn't intersect, then, what can I say about this number? Then this Cj, here now I will need to use the ML inequality. So in this case, we know the magnitude of this number is less than equals to epsilon, right? And also we know that this number does not exceed square root of 2 times the length of square. So why? So this is my square sigma j, and my zj must be somewhere around here, and z is the any point on this sigma on this square. So therefore, the length between this guy and this guy it should not exceed this diagonal side of this square, right? And if this guy is the length of this guy is s and s, so this is the magnitude of this guy, so square root of 2 times s, and the magnitude of this guy is also bounded by epsilon, and so this is the upper bound of the magnitude of the integrand, and I will need to also multiply this number by the length of the curve that is being integrated. And here, but in this case, so this is the length of the curve that we are integrating. So therefore, this is what? Yeah, this is 4 times s. Okay. All right. So this is 4 times square root of 2 times s squared this is case number 1. And for case number 2, if sigma j intersect C, then in this case, this one is, well, again, this is, well, this guy, the magnitude of this guy is bounded by square root of 2 times S. And this guy is also bounded by epsilon. Yeah, this is just as good. S times epsilon. But the problem is the length of this line is the length of this segment. The length of this curve. So, well, what is the length? I want to be somehow really generous about finding the upper bound of this guy. I say this is 4 times S plus Lj. So where Lj is the length of boundary, length of C on Cj. Okay, so, well, for this entire boundary curve, yeah, there must be some part of the boundary curve intersecting with this partial square, right? So I'm going to call the length of this guy to be L of J. So yeah, this guy must be bounded by this number. All right. Okay. So finally, no. Okay, now we are ready to find the upper bound of this number. So this is 4 square root of 2 times, oh, sorry, this one is supposed to be epsilon. Sigma of S squared plus, here I have the same 4 sigma squared times epsilon, and this guy just carries over. Plus square root of 2 times S times Lj. Okay, and everything followed by epsilon. Okay. All right. So what is this? What is S squared? S squared simply means the area of just the tiny little spheres. Okay. And we are taking summation of all over these rectangular covers. So therefore, summation of this guy and that guy. So 4 times square root of 2 times area. So this is a large square area of a large rectangle that contains the region R. So there must be a sufficiently large rectangular region that covers the entire region R. So so therefore, the sum of these areas should not exceed this some certain number, this finite number, and plus square root of 2 times S times the summation of this L. So what is this? Just this is nothing but the circumference of this curve, the length of this entire curve, right? Okay. So I'm going to just say L. And everything multiplied by epsilon. Okay. So what is the conclusion? So that means, well, for the magnitude of this number is bounded by some finite number times epsilon. Okay. So therefore, the only possible answer is this number should be. Okay. I really appreciate your patience. Yeah, this was really tedious and long analysis, but this is some, I guess this is some tax that we actually need to pay once in your lifetime. So yeah, it took lots of work, actually a lot of work to get rid of this continuously differentiable condition, but that will actually later pay off in my next lecture. I really appreciate your patience and see you next time.